Continuing now with section 4.1, let's look at example 2. Find the exponential function f of x equals c times a to the x, whose graph passes through the points 0, 5, and 280. So basically we need to find a and c. A is the base of the exponential function, and c is a constant. We'll see the role that c plays as we look further into this example. Let's begin by noting that the graph passes through the point 0, 5. So if 0, 5 is on the graph, it means that f of 0 is equal to 5. But f of 0 would be c times a to the 0 power. But a to the 0 power would be 1. So that would be c times 1, or c. What we've just established then is that c is equal to 5. So the constant c represents basically the y-intercept of the graph. 0, 5 is the y-intercept. The second point should allow us to find a if we include now the value of c that we found in the first step. So what we have thus far is f of x equals 5 times a to the x power. If the graph passes through the point 280, it means that f of 2 is equal to 80. But f of 2 would also be represented as 5 times a to the second power. So what we have is the equation 80 equals 5 times a squared. If we divide both sides of that equation by 5, 80 divided by 5 is 16, and so we get 16 equals a squared. Taking the square root of both sides, a would be plus or minus 4. However, a has to be positive because a is the base of an exponential function. So from that it follows that a must be positive 4. Therefore, our exponential function that we're looking for here would be written as f of x equals 5 times 4 to the x power. So that would be our exponential function. One thing you can do is put the exponential part in parentheses, and that way there's no misunderstanding that the 5 and the 4 would multiply to give you 20 to the x. That is not the case. By the order of operations, we have to first raise 4 to an exponent before we multiply by 5. So do not write that as 20 to the x power. Moving on to our next example, example 3. Another exponential function. Let Q represent a mass of carbon-14 in grams whose half-life is 5,715 years. Carbon-14 is used in a process called carbon-14 dating, which is used to identify the ages of certain artifacts, for example. The quantity of carbon-14 present after t years is given by Q of t equals 10 times 1/2 raised to the exponent t over 5,715. Half-life, by the way, is the amount of time it required for half of a particular amount of a radioactive isotope to decay. So in the case of carbon-14, that's known to be approximately 5,715 years. Part A asks us to determine the initial quantity of carbon-14. That would be the amount at time 0. So that would be Q of 0, which would be 10 times 1/2 to the 0 divided by 5715. Now, the exponent would be nothing other than 0 in this case. 1/2 to the 0 is 1, and 10 times 1 is 10. The mass of carbon-14 is measured in grams, so the initial quantity of carbon-14 would be 10 grams. 10 grams of carbon-14. So notice that the initial quantity is given by the number that we see out in front, the 10. B says determine the quantity of carbon-14 present after 2,000 years. Well, in this case, that would be Q of 2,000, and that would be given by 10 times 1/2 to the 2,000 over 5715. Now, to make our computation simpler, we can do 2,000 divided by 5715 on a calculator and approximate this. I'm going to change that from equals to is approximately equal. We'll change that to approximately equal since we're just going to approximate that exponent. It's about 0.35. And for the purposes of using a calculator, another way, another way we might write this is 10 times 0.5 to the 0.35 power. So you can enter that in your calculator using your exponent function. And what we would determine from this is that this would be approximately 7.8 grams. So Q of 2,000 would be approximately 7.8 grams. So after 2,000 years, a quantity of 10 grams of carbon-14 would decay to 7.8 grams. The decrease in the quantity of a radioactive isotope over time is referred to as exponential decay. So we can have exponential growth where the function is increasing. We can have exponential decay where the function is decreasing. And the best known example of exponential decay is radioactive decay. One of the most important applications of exponential growth is compound interest. To introduce compound interest, we're going to begin actually with simple interest, which does not illustrate exponential growth, but it will help us in better understanding compound interest. So first of all, what is interest? Interest is the dollar amount that one gets paid for investing money, such as depositing money in a bank, or that one pays for borrowing money, that is, if you would get a loan. The amount of money invested or borrowed is called principal. The interest rate is the percent charged for the use of the principal for a given time period. The amount of interest computed only on the principal is called simple interest. So if interest is computed only on the initial amount of money invested or borrowed, that's called simple interest. There's a simple formula for simple interest. The simple interest formula is the following. The simple interest I on principal P at interest rate R for t years is I equals P times R times t. Interest is principal times rate times time. There's a related formula for what we call the future value for simple interest. That would be the amount that a particular amount of money grows to after a certain period of time elapses. The future value A of principal P at annual interest rate R for t years under simple interest is A equals P plus I. Future value A is principal plus interest. Now from the simple interest formula, interest is P times R times T, so we can replace I with PRT, and then we can factor out P and write that as P times 1 plus RT. So we can express the future value formula as A equals P plus I, or as A equals P times the quantity 1 plus RT. Now for an application of these formulas, let's look at example 4. You borrow $500 for 2 years at a simple interest rate of 12%. How much will you owe at the end of the loan period? The amount that you're going to owe at the end of the loan period is going to be the amount you borrowed plus any interest that's accrued over the 2-year period. So the amount that you owe is going to be the future value. One way that we can determine this is to use the simple interest formula and then A equals P plus I. Let's write down what's given in the problem. You borrow $500, so that would be P, that would be your principal. That would be 500. For 2 years, that would be T, that would be 2. At a simple interest rate of 12%, that would be R, and you want to express that as a decimal, so write it as R equals 0.12. The simple interest formula says that the interest earned over the 2-year period is the principal times the rate times the time. So the principal is $500. The rate is 0.12. The amount of time is 2 years. If we multiply all that together, we obtain $120. That'd be $120 in interest over that 2-year period. The future value, or the loan, the amount that you have to pay back, total amount, would then be the original principal plus the interest. So the original principal was $500. The interest was $120. So the amount that you owe, that you have to pay back after the 2 years, would be $620. Now, a second way that we could come up with this same result would be to use the formula A equals P times the quantity 1 plus RT, as we derived just above. So if we use this instead, again, P is 500, and then we would enter 1 plus R 0.12 times T, which is 2, and that would be 500, and 0.12 times 2 is 0.24, so that would be that would be 500 times 1.24, which again would be 620. So we can come up with the future value directly without computing the interest separately. But just notice in this example that the interest is only computed on the original amount of the loan of $500. So interest is only computed on that, and then just gets added into that at the end of the loan period. So if we extend the period of the loan in example 4 to T years, the future value would be A equals 500 plus 60T. The 60 is coming from P times R. That's this amount right here. So it's 500 times 0.12 is equal to 60. So we get A equals 500 plus 60T. So we see that for simple interest, A is a linear function of T. That is, the amount owed grows at a constant rate over time. The basic form of this is the same thing that we see with y equals mx plus b. Here the m would be 60 and the b would be 500. So simple interest grows at a constant rate over time in a linear fashion. We will contrast simple interest with compound interest as we move to the next video.